Yeah. That's so weird. All right, let's go ahead and get started. So we'll start with some announcements. So we do have kind of, I'll call it volunteer slash club opportunities. And so, again, under the branding of Earth Club, which again, it's more science outreach club, but everybody knows this club is Earth Club. But we have some opportunities planned with the Boys and Girls Club. And so there are opportunities to go out and do demos either on Tuesday or Thursday. And then starting at around 2:30, since obviously that's when like school gets out. And then I think usually they stay until around 4 or so, depending on like cleanup and how excited the children are. Obviously, we have lab during that time, so the day you don't have lab, maybe if you could volunteer, that'd be awesome. We're just looking for a few more people that might want to join. And the goal is kind of to go out maybe like once a month. That's why, like, the more the merrier. That way, maybe you're not going out every month and you can kind of rotate groups or something. And I know tentatively we're like shooting for Feb, like either 8th or the 15th. Somewhere around there is like the starting weeks. So Sam's in the club along with Alexis. I don't see Alexis here today. So y'all can ask them as well, especially if you want to volunteer. All right, let's look at our paper requirements. If I can find those. So I haven't updated kind of the dates, but this is just our goals. So I need to, like I said, I need to update the dates on this. I didn't print out a printout today. Printed out other things, but I'll have a handout on Thursday, but basically I wanted to go over it. It's already posted online, the general requirements. But kind of, again, the idea is we're working on kind of refining our scientific writing and how to write scientifically, so it's less write first person. You're trying to analyze something and make a point. And so I'm only requiring 3 pages of our draft, with the idea being that the full 5-page paper is due spring quarter. So again, we're kind of slowly working towards this goal, trying to make it easy too, so you have a lot of time to get feedback and get help. And so again, right, third person passive voice. So I try to make notes last quarter of that, of people using the I's in the abstract. And so that's where we practice that. So notice, right, we're not doing abstracts this quarter, but instead, right, again, we're focusing on our paper and picking a topic. And so maybe you already did this last quarter, right, with last quarter's writing assignment. If not, you know, if you weren't here, that's fine. That's why we're doing this kind of again. If you now don't like your topic from winter quarter, or excuse me, fall quarter, you can obviously change. Again, that was kind of the point of last quarter, to kind of start looking at the literature, but you certainly weren't married to that topic or anything. And so now I'm kind of asking to, again, pick a topic, reaffirm your topic if you like that topic, and then this is just the general guideline as to how to write a paper. So that being said, there's more than one way to kind of make an argument. It kind of depends, again, what you're looking at. You could be arguing for alternative energies, or maybe against that, and doing some sort of comparison, right, of fossil fuels versus alternative energy. And so your research paper could look a little different, right, of kind of more comparison, compare, contrast, or maybe even like compare if you're trying to compare like 2 papers that maybe point to the same conclusion. But this is just a loose general guideline. So if you follow this, right, you'll still end up with a good paper. But again, kind of depending on where your interests lie, you don't have to stick to this kind of formulaic paper, is what I'm saying. And then, of course, general guidelines, ACS format with ACS citations. So continuing to practice that. And the ACS website has resources for this. So I'll try to post resource guides on all the ACS citation information. And then size 12 font, Times New Roman. So pretty typical there. And then just kind of encouraging you, obviously, to look at primary research. So you want to find a primary research article. Email me if you hit a paywall, and I will try to get it. Usually I can get them. And then it is in the assignment. So if you check on Blackboard, sorry, let me switch this to student view for a second. And so I just updated it. So it should be under week 2 here, and then assignments. And so we have our inquiry topic selection due, and it is due, oops. I meant to make it for the end of the month. I don't know why that didn't change. I'll fix that. But yeah, it'll be due at the end of January for our topic. Okay, well, I'll fix that. All right, questions about the paper or the assignment, just picking a topic. Questions. All right, no questions. Oh, so you don't have to select any topic, you're not just restricted to the topics that are on the paper. I think that was a question asked in the chat. This is just a list of ideas. So solar, a lot of people like drugs. That's always very popular. Anything from like nootropics to other sorts of drugs, right? Cancer, heart disease. There's all sorts of drugs. But yeah, you can do anything and any sort of topic as long as it's loosely related to chemistry. But why I like chemistry is you can really kind of stretch any field to be chemistry related ultimately. So yeah, no restrictions, just as long as it's chemistry themed there. Other questions? Sorry, I'm trying to fix the due date on this assignment. There we go. All right, well, let's dive in to our chapter. So like I said, don't run away from chemistry from this chapter. And so I first wanted to go over, because I feel like your book, it starts off with this picture, and it's maybe not even clear like where these things are coming from. And your book's just kind of like, yep, here we are, and moving on. So let's just kind of make sure we're all, like I said, on the same page with this and what we're trying to understand. And so what we're doing is, again, right, we're putting our atomic orbitals. And so let's kind of backtrack. Okay, so we're looking at hydrogen. And we want to focus on its atomic orbitals. And then combine them, right? So the whole point is we're going to be focusing on diatomics. And so we're going to be putting two atomic orbitals together, right, and getting our molecular orbital diagram. And so like I said, let's orient ourselves and look at what the heck we're looking at. And so, of course, hydrogen is dominated by our 1s orbital. And so just a spear here. And so now we have, right, if we have two orbitals, so we have our other 1s, right, from our hydrogen. So now we're kind of looking at two hydrogen atoms. And I'm just kind of sketching it out for now. And so now we want to put them together, right, to make sort of this bonding combination. And so that's what's shown in our first kind of blob here. And this is called, right, our in-phase bonding combination. And all that's to say is, right, they have a favorable orbital overlap. We can combine them, right, such that they make this kind of overall lobe picture. And so that's all it's showing there, right? So two s orbitals in phase. And this is the same mathematically as if, right, they were both shaded. So that's like the other thing to keep in mind is like, right, that we're not ignoring this. This is just the in-phase combination. And we just normally use unshading, right, to show that they are the same. Sorry, I lost my notes. Not that I need them, but I would like them. All right, so then, sorry, I don't have notes, but that's fine. So then we have the next level up here. And so notice, right, we have a node here. And so this is now showing our out of phase combination. And so now, again, mathematically, we have our unshaded plus now our shaded. So opposite shadings, right? And it doesn't matter whether I had made this one unshaded and this one, excuse me, this one shaded or this one unshaded, right? As long as they're opposite shadings. So now that's our out of phase combination. And so that's where we get our node, or basically, right, our antibonding orbital here. And so again, right, this is our 1s base. And then notice the little notations here. So let's kind of take another step back as to what we're looking at. So write sigma, again, for that head-to-head interaction for those two circles, again, being right next to each other. So that's our sigma, right, or sigma bond. So just make sure we're all clear that this is a bonding orbital. And then that little star there, I know that's kind of hard to distinguish from this picture. I'll redraw it. So a little sigma with a star there. So that denotes an antibonding orbital again, where we have our out of phase combination. And then so really this is the basic orbital diagram, of hydrogen. Let me find my notes. That'll be better. I apologize. I have too many tabs, as you imagine. All right. So then, and we'll re-look at this. But what's kind of confusing and what I don't like is your book. So right, this is basically H2 and analogous. So we'll re-look at this in just 1 second. But then your book kind of went on and was like, let's just show the other orbitals too, right? So that's all that it's showing. And so again, these orbitals always exist. So that's the other important thing to keep in mind. But why your book kind of went ahead and showed them, I'm not really sure. But again, we can just still go over this and understand what they're invoking. And so this orbital, can we guess what this one would be? And so what do we want to call this? What axis here? Yeah, I mean, I like calling it PZ for highest symmetry, right? You could call it PX. Again, we're just defining our coordinates, but yeah, for convention's sake, we'll do PZ. And now we can see, okay, this is still our sigma interaction. So head to head, and then they just kind of, again, oversimplified it, right? We could kind of draw this lobe here, just showing that interaction. And then again, right, sigma bond for head to head. And so now this is showing the anti-bonding combination of those orbitals. So again, just opposite shading. So it doesn't matter if you have this unshaded and this shaded, as long as, again, they're opposite. And again, we have this kind of node here to indicate that, yes, that is an anti-bonding orbital, right? So we have a sigma anti-bonding. Oh, I messed up. So this is, sorry. This is why I was hoping for my notes, but I'm still trying to pull them up. I apologize. This is the s orbital, sorry. So this is just a repeat. So now this is the s focused. So again, they're just kind of repeating our energy levels. So starting with the 1s, then they repeated it with the 2s. So sorry, let me redraw that. I apologize. So 2s, again, sigma head to head. Now 2s, so this is ideally larger if we could draw 2 than our 1s. Again, anti-bonding. And so now we have our p orbitals that it's trying to show. Again, right, they're just showing everything. And so notice they just kind of show the pi interactions. And so we would draw these like so. So px, and again the pi to show the pi bond. Again, the top part has the same shading, bottom part is unshaded, or vice versa. And then it's also, so this is, we'll call it right in the x direction, and then now py going in and out. And again, you can always reorient it, but our through space, right, pi interaction. So from the drawing, it's not very clear, but again, right, they're in two different axes, so py, px, yeah.
So the x and y, they look the same, though the only different one is the z, the p.
Well, and I mean, really the pz looks the same. It's just that it's head to head, right, in that case. So yeah, it's going in a different orientation. And then, so to your point, right, the pz then for our h's end up being head to head. So hence why we get our sigma bond with our pz. And right, how we can tell it's a pz is it has our little node here, right, from our p orbital itself. And right, again, we can kind of draw that in the middle to get our same picture. And then these ones shown up here are our antibonding orbitals. So right, pi antibonding. So now opposite shaded. And again, I'll call this py here. And px. And then this last one up here. So again, mathematically, if we had our in-phase combination, we have to have our out-of-phase combination. And so that's shown up here. And we'll kind of get to this in more detail, but they're trying to show it to us. But notice how small these little lobes are in the center. So this is telling us, right, that electron density is not located here, but rather on the outsides for this antibonding orbital, right? And that makes sense. So if you have an antibonding orbital, then you would not want to have electrons there since that's not favorable. Okay, so that was maybe kind of fast, but does that at least make sense for a overview of what the heck we're kind of looking at to begin with? Yeah.
So the antibonds, are they like repulsing each other?
Essentially, yeah. Or like, we'll basically, well, let's see more what it means, right? So yeah, it's like repulsing, but then it means it's not stable. So kind of with that point, let's first analyze, and we're just going to stick to our small diatomic, so our first row, and that means we're just looking at our 1s orbitals, so we're not looking into the 2 or anything. So let's draw our molecular orbital diagrams for this. And kind of, right, start with your, I'll call it our outline. Right, so this is, again, 1s centered. So kind of just sketch this out. Again, drawing out what orbitals we have. So we're just looking at our 1s. And then mathematically, it's favorable to make a bond where they're in phase. So that lowers our energy. So there's our in phase combination. Then our out of phase. Okay, so this looks good. And so now we can kind of start to fill in the electrons and do this little exercise here and understand, right, what it's all telling us. So let me color code. So let's pick yellow for this H2 plus species. And so H2 plus, so starting with neutral H2, so each one has 1. So 1 plus 1 is 2, but then, right, plus 1, subtract an electron. So now we're only at 1 electron, which is what the chart said. But again, just want to make sure we're all on the same page. And so if we were filling in our chart, so this is what our sketch looks like, right? Our outline, our 1s bonding, 1s antibonding. Then we fill in our electrons, and it's just 1 electron there, right? And so then let's look at what this means when we just have one little electron, right, kind of holding our bond together. So this is just our ground state configuration, again showing the orbital that it's in. So our sigma 1s, so that makes sense for our bonding. And then our little superscript just telling us how many electrons. So just recall our s orbital can hold 2 electrons total. And then again, we only have 1, right, for H2 plus. So we have 1 in there. So our bond order, we can calculate this. So it's our number of electrons divided by our bonds. And of course, we only have 1 electron. Minus 2 times our bond, sorry. So we have 1 electron trying to split it over our bonds. So right, we're supposed to have 2 electrons in each bond. So you can see where the 2 times the number of bonds comes into play. And so that gives us a bond order of half. So kind of implying that that's weak, right? Which that makes sense. So you just have, again, just 1 little electron floating around in that orbital. And the other thing to, again, keep in mind, or your frame of mind, is that we're thinking of probability density. So we're getting our cloud picture. So again, you're kind of imagining this cloud now of our bonding orbital. You have 1 little electron, right, just somewhere floating, moving really fast. So that's our probability density map. And then we're going to have an elongated bond then because of that bond order, right? And it goes back to the trends that we've seen. So triple bonds, right, should be really short. And so if we have this half bond, then that makes sense that it's a little elongated compared to H2. Then bond energy, so it's a little bit weaker, right, compared to H2. But again, we'll see how these other ones compare. So then let's repeat that analysis. So now let's look at H2. So right, 2 electrons. So going back in to our kind of skeletal structure here. So now instead of 1 electron, we would have 2 electrons, right, in our 1s orbital. And so now that's filled. So kind of going back over here. So again, 2 electrons, our ground state. So then we have sigma 1s2. Our bond order is 1 now, right? So we have 2 electrons for our 1 bond. Then our bond length. So now it's 74 picometers. And again, right, so that's just, we would want to compare this to then like all the HH bond lengths or any other hydrogen bond lengths, kind of see what they typically are for single bonds. Notice it has, right, slightly higher energy, so that makes sense because now we have 2 electrons in our bonding orbital. So any questions about this so far? Kind of makes sense. So now let's see what happens. Yeah.
Um, there is another a later section in the book that I kind of confused me as far as the antibonding orbitals. Are those considered technically like a different energy level, like in reference to Pauli exclusion? Like because there was at one point where it was saying that I think it was like a billion or more or something where it jumped up in order to have each one filled before it went to the P. So I was just wondering if that those sigma and the antibonding sigma sigma star or whatever are considered different. Like
Yeah, so how they're drawn is the correct kind of energies and what you're referring to. So yeah, we'll look at that more as to how they fill up. But how they're drawn is, yeah, the 1s sigma, the bonding is lower in energy. And then again, we're just looking at S's. So that's why we fill in 2 electrons first. And then we move up to the next one, which is in this case, right, the 1s anti-bonding, and then fill that in. But yeah, we'll get to your point later and see more examples of that. But yeah, it does matter. And not to go down the rabbit hole, but that's where like all the cool chemistry is like when you either they are degenerate or then you break the degeneracy, right? And then you fill in one at a time and then you get all sorts of cool things, right? And then we can talk about homo-lumo gaps and get really excited. But anyway, sorry, back to where we are. So looking at our diatomic helium then with our plus charge on it. And so again, same analysis. So helium should have 2 electrons, but then plus 1, so we lose 1, so 3 electrons. Again, fill it in. So 1, 2, and then our third one has to go in our antibonding orbital. Okay, so now that's kind of getting to everyone's point of, well, what is this antibonding orbital? So it's obviously, right, an unfavorable interaction. So now that we have an electron in that orbital, let's see what that does. So again, just kind of note the ground state electron configuration. So we have our sigma 1s2. Again, that makes sense since our s orbital can only hold 2. Then our antibonding, again, we filled it in our last remaining electron, so we have 1 there. And so now, let's get a better formula for our bond order. So we have number of electrons in our bonding minus our electrons in antibonding divided by 2. And so looking at that, well, we have 2 electrons in a bonding minus 1 in an antibonding. So now we're at 1 divided by 2. So that's why we have a half bond order once again for our helium 2 plus. And then with that, again, another elongated bond length. That makes sense. If you have something in the antibonding orbital, right, again, that's unfavorable, so they're going to want to be a little bit further apart. And we see that again in their bond energy was weakened. And then we can take that a step further now, looking at diatomic helium. And now this is showing us why, right, it doesn't even exist. So not even in the gas state. So if we go to fill in, right, our 4 electrons. So starting at the bottom, so 1, 2, 3, 4. Well, notice that, right, we have just as many electrons bonding as we do anti-bonding. So 2 minus 2 obviously equals 0. And so that's why we get a bond order of 0, or basically saying, right, that this does not exist. And so now we have a better understanding of why helium-2, right, does not exist. So that antibonding orbital, again, that's unfavorable. So unfavorable interaction, so it does not exist. And so question, So I think it goes back to the question that was asked earlier. It's just the order of the energy diagram. So that's why we have to fill in this 1s antibonding first. So going back to hydrogen, I think this explains it, right? So again, in terms of energy level, 1s is the lowest, then it's the 1s antibonding, then it's the 2s, 2s antibonding, and kind of so forth. And we'll see where it's not as straightforward, but yeah, going back to Pauli's exclusion, you have to do the lowest energy orbitals first, and then keep going up. Okay, questions? Just making sure we're not going too fast either. All right, so now let's look at our, we'll call it our second row diatomics. And so now we're going to start with what I call our generic picture, just like we did initially, right, with our first row. But now we're going to look at our simplest scenario. And so what I mean by this is we have currently no sp mixing. So we'll get into what this means and when in just a second, but let's start, like I said, with our second row. And so let's just take our generic A2 compound. Again, this is for no sp mixing. And so we want to just do like we did before and outline our orbitals involved. Since we're on the second row, I'll mainly focus again on our valence electrons. So that means we're looking, and I'm trying to give myself enough space. So I'm going to put the 2s orbital down here. And so I wrote it out, and then I always like putting a picture of what it looks like again, so I know it's mixing visually. And then we put them, if they're the same atom, you put them at the same height. Otherwise, you put the more electronegative one lower. So 2s, again, right, looks like a blob. And so now I'll just start our mixing picture and drawing out my molecular orbitals in the center. And let me sketch out, so our 2p, so 1, 2, 3. And just kind of put that on the side, so 1, 2, 3. So again, right, our p is higher than our s. And so now let's look at all our combinations. So of course we have, right, our favorable in-phase combination. So now this is our 2s sigma, right? Again, our direct interaction. And then to our earlier question, our lowest energy right now that we're focusing on. Obviously we have our core, right? Our 1s is down there, but we don't care about that right now. And then mathematically we have to have our antibonding combination. So different shading. So now 2 sigma antibonding. And so now we can continue. So the next one in energy, so next lowest, so now we're thinking about favorable interactions. And so this is going to be our PZ again, as we're calling it. So in phase PZ, and then sigma, right? So we're identifying again that it's a direct interaction. And so that's again why it's the next one in energy, since that's favorable, right? And then our next one is going to be our 2 pi interactions. And so I try to draw them right next to each other. You could also draw them like so, if that makes you feel better. So either, again, really tight or right next to, so we can see that that's, again, degenerate. So this is our pi bonding. And then, again, that's going to be px, py. So again, they're degenerate, meaning they're the same energy. They're just different orientations. And so then our next one in energy is actually now our pi antibonding. So right, since they have this kind of through space interaction, when you have the antibonding interaction, it's almost like not as bad, so that's why it's not as high in energy. And so then we have, again, our two degenerate px, py. Oops, sorry, that shading came out off. There we go. And then our last molecular orbital here is now our most unfavorable interaction. So now it's our PZ sigma antibonding interaction with, again, our shading being opposite in the middle there. And so then we could draw little lines too, just kind of showing where they all came from. And so other just quick sanity checks. So however many atomic orbitals you mixed in, that's how many molecular orbitals you should have in the center. So we have 1, 2, 3, 4, 5, 6, 7, 8 atomic orbitals. So 1, 2, 3, 4, 5, 6, 7, 8. So that matches. So that's good. All right. So again, just double check yourself on there. And so now let's practice, right, how this would go. And so this is really like your answer key too for a lot of the quarter, right? And well, let's look at our notes. So we'll, like I said, we'll do SP mixing in a second. But all we need to understand is when we do mix and when we don't mix. And so right here is where there's a change or a shift. And so past nitrogen, there's no SP mixing. And so we'll look at nitrogen now to understand kind of why there is then. But let's just practice that. So let's look at, we'll look at fluorine. So let's do fluorine and just see if you can rewrite this diagram for a second. So go back to your generic picture, probably redraw it, right? It doesn't hurt to kind of redraw it, especially while you're learning it. So I would kind of keep one as your clean copy and then just kind of practice redrawing that. See if you can draw our molecular orbital diagram for fluorine, right? What does that look like? Can we get the bonding order? We're essentially just filling in this diagram, but again, good time to kind of practice it right now and just kind of feel comfortable with the little pictures. And I would practice the little pictures even if they feel like chicken scratch now. Eventually, when you move to higher orders of chem, they will be helpful. So hopefully your diagram looks something like this. And then, right, just keep track of what electrons you're filling in. So we're only looking at the valence electrons, right, in this case. So 14, so 1, 2, 3, 4, 5, 6, and then make sure we fill our degenerate orbitals correctly, right? So 7, 8, 9, 10. So sorry, I lost track. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 there. So does that look like what everybody got for our diagram? And so some things to point out then. So now looking at this orbital diagram, we can note what's called our LUMO. Or sorry, not LUMO. HOMO. So HOMO stands for highest occupied molecular orbital. And so that'd be something that you want to identify. And then, again, I probably have said this in passing, but this is where it comes from, this HOMO-LUMO gap. And so LUMO is lowest unoccupied molecular orbital. And so again, right, kind of thinking back to the previous quarter where we were looking at flame tests or excited states. So right, this is why we care about this HOMO-LUMO gap. So this is where pretty colors can come into play, right, depending on what this HOMO-LUMO gap looks like. So that dictates, right, what sort of transitions are available and et cetera, et cetera. So that's why chemists always care about this HOMO-LUMO gap and how big it is and all sorts of things. What orbitals are involved, because that's also telling you what two orbitals are kind of readily available as well. All right, questions on this one so far? This makes sense. Ask a question. You're talking about this one? Yeah. And so again, it's because of like mathematically how like this is basically more unfavorable, right? Because again, it's a head-to-head interaction. So when they're opposite shading, that's more unfavorable. So that's why it's higher in energy versus, yeah, the through space ones. Other questions on fluorine? All right, so this might actually be a good spot to take a quick break. So maybe let's come, well, we'll just call it come back at noon roughly. And so we'll do SP mixing after our break then and see how to treat that. All right. Did we all make it back from break okay? So I did post a link in Blackboard. So quite a few people have been asking me about like the math kind of behind these cryptic pictures. So I posted a link. Luckily, this whole book is available online, Orbital Interactions in Chemistry, but this one is a really nice book. So this may give you at least some math background and really the whole background of this is a true inorganic chemistry book, but it gives us again the math and the background for the pretty pictures. And so right, it goes into all the math. So if you want to knock yourself out and look at this, it is posted for your pleasure and enjoyment there now on Blackboard. All right, any questions crop up? I don't want to go too fast because otherwise, like I said, I'll get overexcited. Anyways, oh, one thing that I forgot to do. Somebody did remind me of this. So we didn't calculate our bond order, which we should have done for F2 for fluorine here. So our bond order. So let's count up how many electrons we have in bonding orbitals. So we have 1, 2, 3, 4, 5, 6, 7, 8 minus 1, 2, 3, 4, 5, 6. So 8 minus 6, so 2 divided by 2. So that gives us a bond order of 1, right, which is a single bond, which is what we, right, predicted from just kind of a general Lewis dot structure. And so that's the other thing that we're kind of getting at is, right, is this Lewis dot structure truly a good depiction? And we're kind of comparing that, right, to our MO diagram and seeing what additional information we can gather. Questions? Okay, feeling good so far? All right, so now let's look at our SP mixing scenario. And so, right, again, we kind of have our answer here. So this is, right, we have to invoke SP mixing. But let's understand, well, what is SP mixing? How do we kind of get this order? What changes? And why? So let's go through that. Hopefully I didn't lose my notes again. Oh, geez. Sorry, I don't know how I managed to do the same thing I did last time. I pulled up a different tab and lost my notes. Okay, there we go. And so now I'm going to kind of make our generic, right, A2. Kind of generic, but now with SP mixing. But before we just kind of, again, start chicken scratching these little pictures, let's try to understand what's happening and what's going to mix. So first of all, what do you guys think is going to mix? What's kind of right prime for SP mixing? So, well, the sigma bonds, but which orbitals? Which ones are? Yeah, the Z, right? So, okay, so let's think about that. So, yeah, we're going to mix our kind of 2s, right, with our now our PZ combinations. And I'm just kind of drawing them a little generic so far, right? So I haven't quite gotten the shading all flipping. But basically now we're asking, okay, let's take these two orbitals, because like you guys are noticing, well, they're in the same sort of line, right? They're both that sigma head-to-head interaction. So yeah, that would make sense that they might want to mix there. So again, let's look at that. And so the thing that we want to think about is, well, let's think about kind of our best combination where everything is mathematically in phase, and that's going to give us a nice bonding happy orbital. and then versus kind of the worst one, and then we'll figure out the other orbitals kind of in between mathematically. And so obviously the best one is kind of how I drew it. And again, right, why it's the best is because all the shading matches. And in this case, how I've drawn it, right, we have the unshaded part all in the center. And if you could kind of imagine, right, just like combining that. So we have, again, our Z's that are unshaded, and they would be magnified by our S's that are unshaded. And we'd kind of get this, SP mixed orbital here, where again, our electron density has been kind of maximized in the middle to make our super good bonding scenario, right? And so we'll see this in a second when we redraw our diagram. But this is part of the point of SP mixing, as this is now effectively lowered, right, that molecular orbital. So that's more bonding, more favorable, so now that's lower in energy. All right, so that's good. Obviously, though, now we also have to pay a price for this. And so the absolute worst is, of course, trying to maximize the shading opposing in the center. And so that would look like where we have our two s orbitals out of phase. And then what if they added with our pz orbitals that were also out of phase, but we're in phase with the bad combination such that we're making it really bad in the middle, right? So this is basically really anti-bonding. So, right, that would be pretty unfavorable to have these two anti-bonding regions, again, next to one another. And so just thinking about this energetically, so we paid the price then. So now this one is higher in energy than any of your unmixed orbitals, right? Because again, in the middle, more unfavorable interaction there. And then our last ones is we kind of have to come up with our next bonding scenarios. And so this one is now, so I'll just kind of call them our middle ones. And we have, right, our in-phase combination where our s orbitals are in phase. And what if we had it so where, oops, sorry, I drew it wrong. Where the pz orbitals, right, are in phase. So this is, right, a bonding combination. However, they're out of phase with each other, right? So you could see that if you were to put these kind of circles together, like this circle would cancel out this circle, make that region of less electron density. And so that would give us something that looks something like so. And the point is being the electron density is again on the outside, and we have less electron density in the middle here. So while this is formally a sigma bonding, sometimes you might see this as kind of more of like a non-bonding orbital, and some people may indicate it as such because again there's not a lot of interaction there, right? The electron density is more on the outside. And then our other combination that's unfavorable but not as unfavorable is, well, what if we had our out of phase combination and we added it with another out of phase pz combination, but such that the middle parts canceled each other out, right? So now we have this anti-bonding orbital, but we're kind of minimizing that middle interaction. So now we get something like so. Again, it's still anti-bonding, right, formally, but this is again going to kind of be more of a non-bonding orbital where again our electron density is on the outside there. And so again, we can kind of take a step back as to why SP mixing happens. So we have this really favorable combination, which we're going to see, and then we kind of minimize, right, these interactions. so that we have kind of these non-bonding interactions. So we don't have this anti-bonding being so unfavorable. But then again, obviously, we had to pay the price somewhere. And so now let's look at our order of things and see how this changes. Because it does change, again, the order of our orbitals. And so again, right, this is our answer key. But let's figure out kind of what switches. And let's point it out. And then we'll go through it. So looking at our not mixed one, so again, glancing at it, O2, so we have our sigma S2, then our anti-bonding, right? And then we went to our PZ1. And so now we've mixed our PZ, right? So we're still going to have, and let's do that. And so now we'll do the same sort of thing. So I'll have generic A, but now we're doing with mixing. So with SP mixing. So I'll still lay out, right, my 2p. So we're still mixing our same orbitals like before. So 2s. And so we start off, again, pretty similar, except now we're doing an sp mixed orbital. So we have, right, our mixed 2s. So again, our most favorable combination that looks like this. So technically, right, it'd be a little lower. So favorable electron density in the middle. And so again, that's our sigma orbital from our head-to-head interaction. And then the next one, the next is going to be, right, our formally anti-bonding orbital, right, just like before, except this is the one from sp mixing where, again, we've minimized that electron density in the center, right? So we've kind of taken that unfavorable anti-bonding and kind of minimized that. So yes, it's still anti-bonding formally, right? But again, we've minimized that electron density, so that's good. And so now let's think about what's next. And so we're kind of deciding between either this kind of non-bonding orbital, or let's not forget, right, we still have px, py. And so this is where the switch, as it's called, kind of occurs, is because now this is more non-bonding, right? It's not as favorable of an interaction. So the next orbital is actually, right, your pi bonding orbital. So px, py. And so those are, again, degenerate. And so let's go back to, I'll call it our answer key. So that's what's shown here, right? So notice the switch. So now we went from our anti-bonding s orbital to now our pi bonding. So that's interesting. So again, right, note the switch. Right? So different order there. So just keep that in mind. So yes, our pi is next. And then now we can do, right, what's more of our PZ, but really it's kind of our sp mixed non-bonding orbital. And from our minimized electron density. And so now that's next. And then we can continue. So then we have our pi anti-bonding orbitals, just like before. Sorry, screwing up my drawing there. And then we do have, again, right, our highest molecular orbital is now our worst bonding combination. So where the electron density is in the center of the anti-bonding. So again, most unfavorable interaction. And then double check yourself. Make sure you still have 8. So 1, 2, 3, 4, 5, 6, 7, 8. So yes, we still have 8 molecular orbitals in the center there. And so now that we have, right, our template, we can practice and kind of fill these up like shown. Let's do, so yeah, let's try one. Let's just do lithium. So now try out diatomic lithium. And again, right, I might keep this one as your generic template so that you always have this reference. And then go ahead, right, practice rewriting it. Again, we are invoking SP mixing. And so on an exam, if it's a diatomic like this, right, like lithium, beryllium, boron, I would expect you to look at your notes, right, and know whether there's SP mixing or not. If we were to have something tricky, like let's just say CO, then I would tell you whether to invoke SP mixing or not if it's something that's not clear. So does that make sense? So yeah, I only expect you to know mixing on the diatomics, and then I will specify SP mixing or not. So yeah, go back to your lithium, see how your sketch is looking. So double check your sketch. Again, I just like drawing the pictures so we're all clear as to who's being mixed and what the orbitals look like. And then note we're just focusing on our valence electrons. So lithium, right, just has one valence electron. So I put in our 1 there. And then we'll start from the bottom. So 1, 2. And then that's it there for lithium. And then we could do, right, our bond order. So we have just 2 electrons in a bonding orbital. So 2 divided by 2. So we expect, right, 1 bond then for lithium diatomic. So that looks good. So now go ahead. Let's see if we can draw out. Let's prove why diatomic neon doesn't exist, right? So go ahead. Now I'm skipping around. So look at neon, right? Think about whether it has sp mixing or not. So that's your first question. And then see if you can draw our diagram. We'll compare. So looking at neon again, right? No sp mixing, and I didn't really explain why. So why that is our s orbitals get further away from the p's as we go down to these more further elements down the row here. So that's why we don't have sp mixing anymore. And so then, right, just go ahead and sketch out our usual diagram without sp mixing. Yeah, question?
For the PV sigma, like energy level, is that the count is below the PX and the PY, and then if there is mixing, is it above their flip?
Yeah, exactly.
Mixing and non-mixing?
Yeah.
Or sorry, I said it backwards.
But yeah, if it's not mixed, the PZ is below, right? Because it's more favorable. So yeah, there's our PZ, sigma, and then our pi bond. Yeah, basically when we mix, right, it's just because we've dropped this so much lower in energy, and then that affects the middle ones, and that makes them more kind of non-bonding, shifting them higher. And then pi anti-bonding. So 1, 2, 3, 4, 5, 6, 7, 8. So again, always good to count, double count. And then how many electrons do we have in diatomic neon? How many valence electrons? So 16, right? And we could fill them in on here if that makes us feel any better. And then what do you notice when you fill in all the electrons? So then what's our bond order for neon?
Zero.
So it should be 0, right? That's what we kind of expect. So let's see. We have 1, 2, 3, 4, 5, 6, 7, 8 in bonding, minus 1, 2, 3, 4, 5, 6, 7, 8 in anti-bonding. So yes, 8 minus 8 divided by 2 is 0. So yes, that is why diatomic neon has not been observed, since it can't hold itself together, essentially. Question? Just dividing it by two because each bond is two electrons, so that's just a formula. All right. Yeah. So now let's look at some other diagrams. So let's see if we can draw out nitrogen. And so nitrogen, if you recall, that's the last one. So it does have sp mixing. So go ahead, draw that out. So double check your structure. I just kind of sketched it out. Again, things to note is your PZ, right? How it shifted. So it's now higher than our pi bonding since this is more non-bonding essentially. And then filling in our electrons. So 5 valence electrons. So 1, 2, 3, 4, 5, 6. Did I do that right? 1, 2, 3, 4, 5, 6, 7, 8. Oops. 9, 10. Forgot my electrons there. So now that should look better. And so now we can calculate bond order. So we have 1, 2, 3, 4, 5, 6, 7, 8 in formally bonding minus our 2 in our formally anti-bonding. So 8 minus 2, 6 divided by 2 is 3. And so far, right, this agrees to with our Lewis dot structure, right? So we could draw out our Lewis dot structure. So 1, 2, 3. So that looks good, right? That's all kind of matching with what we find. What's also kind of interesting is, right, we have our PZ, kind of this mixed non-bonding orbital showing us our electron density is more on the outside. And that does, again, kind of match with our picture of our Lewis dot structure here. So other things to note. So this is, again, our LUMO. Oh, sorry, I did it again. I don't know why I keep getting it backwards. HOMO, highest occupied. And so again, right, this has implications for bonding. So nitrogen can bond at the PZ. So that's interesting. And then again, right, our LUMO is available for bonding potentially. So we could accept electrons, so that's interesting. So now let's look at it and compare it to oxygen. And so let's see if we agree. So we have a question in the chat too about yes, we expect a bond order of 2 to be a double bond. So see what we get for oxygen. Let's see how it compares. And again, oxygen would have no sp mixing. So practice drawing that. I'll rewrite that as well. So no sp mixing.
So the sp mixing only occurs for nitrogen then?
Yeah, for nitrogen, carbon, boron, beryllium, lithium. So nitrogen on down is sp mixed.
But the other ones don't have enough electrons for it to make a difference, right?
Yeah, but yeah, exactly. But yeah, you still want to know because you still want to get the order correct of these lower ones, even though it doesn't matter. So start looking at your drawing. Note the position of the PZ right above our 2s antibonding. Again, since we're not doing mixing for this one. And so let's fill in our electrons. So 6 valence electrons. So 12 total. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have 11, 12 there. So that could be interesting. And so now let's look at that. So what is this telling us about oxygen? Do you remember? There's a certain term for this, but I don't know if you remember it. Yeah. Yeah, so paramagnetic. Excellent. And so let's redefine it. So this is paramagnetic. And this is basically when we have unpaired electrons, right? So in this case, we have 2 unpaired electrons here. And this is compared to the definition of diamagnetic, which simply means, right, we all have paired electrons. So typically most compounds are diamagnetic, right? That's what we kind of expect. And we don't generally see a bunch of radicals, so we expect most of our electrons to be paired. So again, right, there'd be in our bonding orbital like that. And so what's going on here? What is this showing us? And then, right, what does this kind of mean? And what's kind of fascinating is if we go back to our Lewis dot structure for a second, just sketching it out. All right, so we'd probably get this for a Lewis dot structure. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And okay, our TET rule satisfied. But then looking at this, right, it doesn't, there's no evidence, right, that this is paramagnetic. Everything looks nice and paired. And so it's not obvious that it's paramagnetic until we come to our MO diagram. So that's what's pretty powerful about this MO diagram, is that it's telling us it's paramagnetic. So I'll probably start off class then on Thursday doing our liquid nitrogen demo of this, so you can actually see that yes, oxygen is paramagnetic and what properties make it such. So we'll see how it sticks to the magnet because of its paramagnetism. So that'll be fun.
Being paramagnetic is why things like hydrogen peroxide can exist.
I don't know about that. I hadn't thought that far. I mean, it's just like the peroxide itself is like a different sort of shape too. But that could be something we think about at another time. But yeah, the main thing is that it's paramagnetic, but again, our Lewis dot structure implies that it's paired. Yeah.
Because it has a full like P2 sigma bond, but it has no like antibonds.
Well, it's just that this antibonding orbital isn't filled, right? So because it's degenerate, so then it puts it into 2 separate orbitals, right? But then that gives us our unpaired electrons, right? And then so anytime we have these unpaired electrons, that's when they can be influenced by a magnetic field, for instance. But yeah, we'll revisit this more on Thursday at least. But let's look to kind of wrap up our question in the chat too. Well, let's look at our bond order and see how it at least compares to our Lewis dot structure. So let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, right? In bonding minus 1, 2, 3, 4. So 8 minus 4 is 4 divided by 2. So we do get a bond order of 2, right? So that still at least agrees with the information we found in our Lewis dot structure. Again, the only thing that was kind of lacking is this paramagnetic property there. Questions on that so far? Let's do another practice just because We still have like 10 minutes. So let's try one for fun. So I had hinted at it. So let's try CO. And so CO, I will tell you, involves SP mixing. And so see if you can come up with your molecular orbital diagram for CO, again, given that there is SP mixing in there. So I'm just going to start sketching it out as well. And then I am, again, this is all, right, a little relative. So this is where computational chem also has a lot of power and fun, and like where the interesting part of computational chemistry can also come into play is how much mixing you're invoking and how detailed, right, the computational chemistry gets. But that's what's pretty cool, is again, right, it's giving you kind of a picture to this. So that's what I'm attempting to show, by the way, is since oxygen is more electronegative than carbon, I try to show that by putting my orbitals a little bit lower. And again, that's kind of detail. You guys can work towards that. And so again, SP mixing. So we just want to get our order correct. So obviously that's our most favorable one. Here's our formally antibonding, if I could draw it correctly. And then our degenerate pi bonding orbitals. Then our kind of non-bonding-ish pi interaction, pi antibonding. Sorry, non-bonding. I meant to say sigma, right? Sigma from head to head. I kind of misspoke and said pi because I was thinking of PZ, but right, our SP mix, kind of sigma, formally non-bonding, essentially interaction, then really unfavorable. So let's count our electrons. So again, we're just looking at our valence electrons. So 1, 2, 3, 4 for carbon, and then 6 for oxygen, giving us 10 electrons. So just filling that in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so again, right, this tells us interesting information. So we have our HOMO once again. And so we kind of saw this with our Lewis dot structure, right, of CO. So again, just kind of sketching the Lewis dot structure back out. And we had said, well, carbon, well, CO typically attaches at the carbon, which is kind of odd. And then now this is showing us, right, back of the envelope, calculations of that orbital. Again, it's primarily on that PZ, right, and electron density is on the outside. So that, again, just kind of reaffirms what we knew from our Lewis dot structure and also reactivity. And then why I keep pointing out the HOMO-LUMO gap is, of course, we'll later see like what else this can do. So like I mentioned, right, our HOMO, this is showing electrons donating and kind of where that's coming from. Again, when your carbon attaches, such as to a metal, right? So our carbon, so attaching, so it would be attaching right from this orbital. And you could even start to think about or like how you're going to take this further in your higher level classes. It's like, okay, this is the orbital, right, that's interacting with my metal. And then I've mentioned it before, and I'm going to mention it again, this phenomenon of pi back bonding. And so now we can see it again of where this is coming from. So we have, and let me pull up a better picture. And this is, again, where computational chem comes into play. But I just really want to emphasize what these orbitals look like. And so again, they're the LUMO, lowest unoccupied. They're empty. They're primed, right? They look like this. And so if I redraw this in this orientation, they kind of look like a d orbital. And so now you can see how later, when they come to this metal, okay, well, you have your PZ, right, donating. There's your sigma bond. And then you have this additional pi back bonding stability where the metal is then donating back to this LUMO, right, of our CO, which adds to further stability with these CO complexes. And so again, right, the point is you're just kind of seeing, I have this picture, right, those are my electrons donating to the metal, and this is my empty orbital that allows for this pi back bonding interaction. And just slowly starting to piece those pieces together, right, pictorially. So hopefully that's making sense. So we'll end here for today. Like I said, we'll pick back up on Thursday, and I'll really prove to you that, yes, oxygen is paramagnetic, and oxygen is blue. We'll see that it is actually blue. And then we'll look at more sp mixing and so forth. So we'll go back and kind of look at these sp mixing orbitals again, and hopefully feel really good about that. All right, let me know if you have questions. And then, like I said, if you want to meet for office hours Wednesday or Friday, I can do that, but just email me so I know when to be sitting in my office exactly. And then I'll see everybody for a lab. So I'll stop this stream for now. Thanks, everybody. Just email if you have questions.